When we first learned about similar figures, or in this case, similar solids, because we're talking three-dimensional shapes, we learned that similar means that objects have the same shape but different sizes. So today we're going to take that concept of same shape, different size, and we're going to relate it to surface area and volume. So what we're going to discover in this lesson is how surface area and volume are affected when you change the size of a shape. So to fill in the blanks up top, similar solids are solids that have the same shape. And now we're going to write in that they have proportional corresponding dimensions. So what we need to do is remember back when we did similar figures, we talked about how we could create a proportion from their side lengths. So that's why we filled in proportional corresponding dimensions. So in order to figure out if something is similar, we would create that proportion like we did several chapters ago and see which one is true. So we've got cylinder A over here, and we want to see whether cylinder B or cylinder C is proportional. This is our starting cylinder, and then these are the ones that we're trying to match up. So we have to create a proportion to see which one is true. So I'm going to start off with 6 over 4 because that's the proportion that I would get from cylinder A. And then I want to see if that's equal to the corresponding dimensions of cylinder B, which would be 5 over 3. So is that true? Is 6 over 4 equal to 5 over 3? Hopefully you're saying that the answer is no. So hopefully it's cylinder C. Let's just make sure. Does 6 over 4 equal 7.5 over 5? Now we hope that this is true, but multiply and confirm. When you do your cross multiplication, you'll get 30 from each side. And so this is a yes. So the answer is cylinder C is proportional. So that makes it a similar solid. So now we have a missing measurement, but the technique is the same. So since they're telling us that they're similar, then we know we can make a proportion. That's the key word for proportion, similar. So let's set up a proportion, 5 over 13, and you have to match up the corresponding side lengths or dimensions. So 5 matches with 7, and 13 matches with this script L. That's a script letter L. So pause the video and solve. Hopefully it didn't take you long to calculate that. It's 18.2, and we're talking yards, so that's our answer. Now this picture over here where it lists all the different shapes, it's just so you know all the different things that are called linear measures. Linear measures are just one-dimensional measurements. So this is just a picture of lots of different shapes that you've learned up until now, and it shows you all the different linear measures. So we've got the height, we've got a radius, we've got length and width, lots of different linear measures. The relationship that they have with surface area is that when you take the proportion or the ratio of the linear measures, so in this case we would take A and B and set them up in a ratio, when you square that ratio, you get the relationship of the surface area. So if you're highlighting, I would encourage you to highlight this right here and then maybe this title that I boxed earlier, because that's an important relationship. When you square the ratio of the measurements, you get the ratio of their surface areas, which hopefully makes sense to you because area is a square unit. So let's use this in practice. We have to find the surface area. So they tell us that these two pyramids are similar, and we have to find the surface area of pyramid A. Now you luckily don't need to know the formula for the surface area of a pyramid. You could, it might help you if you were stuck and you needed to use a different technique, but we can use the technique that we have in our sample up above that tells us that the ratio of their heights, which in this case will be 6 over 10, when you square that, you get the relationship of their surface areas. So 6 over 10 squared is 36 over 100. So this is the relationship, this is the ratio of their surface areas. This is not their actual surface areas. This is just the relationship of their surface areas. So now I'm going to take this ratio, 36 over 100, And now I'm going to say, well, it's not actually 36 and it's not actually 100. It's actually something I don't know over 600. So I'll just erase that question mark and put a variable because that's what we do in mathematics. And now when you solve this, you should get that it's 216. And now we need to we're talking surface area, so we're talking about a two-dimensional measurement, so it's square feet. We have another cool relationship where we talk about the volume of solids. So the volume of solids relationship is when you take the ratio of their measurements and you cube it. And this might make sense because volume is a cubic unit. So it's very similar to the surface area, but instead of volume, we're going to take their ratio, which in this case would be A and B. And when you cube it, you get the relationship of their volumes. So again, let's see how this works in practice. We're going to find the volume. We've got this touch tank at an aquarium, and they're doubling the dimensions. What is the volume of the new touch tank? So I'm going to draw a picture, because a lot of times the best way to start a geometry question is by drawing a picture if there isn't a picture drawn. So I'm just going to sketch a tank. There we go, and there's the water. Fantastic. All right, here we go. Now, this is an example where you think to yourself, okay, I've drawn a picture, and they still don't give me really much of any information. The only thing I know is this volume, and that's it. But they do tell you that it's doubled. So, in theory, it doesn't matter what the tank started out as. All it matters is that when you get the new tank, it's doubled, because the ratio will be the same, right? 1/2 is the same as 2/4, which is the same as 5/10 or 10/20. They're all the same ratio. Remember, we're just talking ratios. So let's make it simple. Let's make this 1 height, and then this will be a 2 height. You can make it other numbers if you want, but I don't see why you would make it more complicated. This new tank is double the old tank. So this ratio, 1/2, when you cube it, you get 1/8. That represents the ratio of their volumes. So let's take that ratio, 1/8, and make it equal to the real volume, which is 2,000 on the smaller side, and then I don't know what this is on the larger side. So when you solve this, you get choice D, 16,000. All right, the next couple of examples are on your own, as it says. And if you need help, it will also tell you what example to go back and look at. Pause the video and try these on your own. All right, so in this example, you needed to actually do two different rate proportions because they gave you a 20 and an 8, and so you had to make one proportion to find the W and then another proportion to find the L. You can't solve it all in one step. There are two different dimensions, so you have to do two different proportions. Let's move on to the next on your own example. All right, if you haven't already tried this one on your own, pause the video now and try it on your own, and again, check example 3 if you need help. All right, remember that the ratio of the lengths is, when you square it, you get that's the ratio of the surface area. So I took the ratio of the surface area and turned it into a proportion and solved, and I got 237.5. And I also want to point out that this is square meters because it's surface area, and area is a square unit. So your area needs a square label. Try number 3 on your own if you haven't already. Remember that the ratio of the measurements cubed equals the ratio of the volumes. So I took this ratio and I turned it into a proportion, and I solved 20.8 centimeters cubed, or cubic centimeters is a better way of saying it. And remember, it has to be cubed because it's volume, and volume is a 3-dimensional measurement. If you have any questions, write them down and ask me when you come to class.